All right, good morning and welcome. Lecture 3, Friday is already here. All right, let's pick up where we stopped. Were there any questions before I begin today's class? Okay. Let's see, sharing, new share. So we stopped here. Okay. Fluid flow analogy for electrical circuits. Let's say we have a pipe with carrying some fluid through it. We have a direction of the fluid flow, and also depends on the pressure at either end of that pipe, right? And so an analogy can be made with an electrical conductor. If you have an electric potential difference at either end of that conductor due to an applied voltage or source or element or whatever in the circuit, then we would have current flow. Current always flows from high to low, like everything. Okay, always goes from plus to minus, except when it's a source. So if you have an electrical conductor and it's part of a closed loop, then you can have current flow through it because of a potential difference or a voltage that is being applied some part of the circuit. Conductor or a wire would be analogous to the pipe that is carrying the fluid or the medium that is carrying the fluid. The fluid itself can be analogous to a current, and we have a direction of the flow of the current, right? An electrical switch is portrayed with this kind of symbol. So this is an electrical switch. We will use electrical switch for certain analysis problems when we come to capacitors and inductors in chapter 4. Okay, but here's the big difference between a valve and a switch. A mechanical valve, when closed, will stop fluid flow, right? In most cases, if a valve is closed, it'll stop the movement of the fluid. And so this is, of course, mechanical valve, when closed, will stop the flow of fluid. So let's write down valve and electrical switch. Closed, open. Is this switch closed or open? It's open. Okay. A closed switch is either noted by a time or it would simply be something like this. Right? Now, current always needs a closed path to flow. If the pathway is open, current is not going to flow. And the most common example is right in front of our eyes, the AC electrical power outlet. Okay, a power outlet is an open loop. It is not closed, so current cannot flow through there. If you take a piece of wire and you stick it between the two openings in an electrical outlet, what's going to happen? Spark, small explosion. The reason is you have high voltage coming in there. The wire has some amount of resistance, but now you have provided a closed pathway or a closed loop for current to flow through. So if current flows through, it generates voltage, it generates heat. If the wire is very thin and cannot handle that heat, it's going to blow out, right? That's the functioning principle behind an electrical fuse. The fuse is made of a thin wire. It has certain rated capacity. If the current flowing through that wire exceeds the limit, it's going to blow out. And then it's going to interrupt the flow of current. So a switch, again, provides the function of either allowing the current to flow through or stopping the current from flowing through. A switch when closed, will allow the current to flow through. Again, there's a physical pathway for electrons to move. And so a closed switch will permit flow. An open switch, which is what you see here. So this is open. This is closed. So an open switch is going to block the flow. A closed valve is going to block the flow. A closed electrical switch will permit the flow. And an open valve will permit flow, but an open switch is going to block the current from flowing. And that's the difference between a mechanical valve and an electrical switch. So you might have been used to terms like open valve, closed valve, but here when we talk about switches, an open switch and an closed switch means exact opposite. So I just like to point that out to students. Okay, make sense? All right. When we first begin circuit analysis, we have no idea what the voltages are across any element. We have no idea what the current flow is across, through an element. Okay, so we make assumptions and we assign values to the current and the voltages randomly. So you see some current directions here, you see some voltage polarities in this example. These are assigned at random, completely arbitrary. Okay, these are completely arbitrary. We assume these current directions and these voltage polarities, but that assumption is based on certain logic. Okay, the assumption is based on certain logic, meaning if we know that a power supply is connected to the circuit, the power supply is, the polarity of the power supply would be given to us, right? And so we can assume the direction of the current flow from the source, and then we assign randomly to the rest of the circuit. But again, when we assign those, they are based on certain assumptions, and the assumptions are based in logic. But the point remains the same. When you begin your analysis, we have no idea what the voltage polarity and the current direction is in the entire circuit. We just assume a polarity and a direction, and we begin our analysis. Okay, so you assume voltage polarity and current direction, but the assumption is based on logic. Logic and, of course, rules that we will learn about. Okay. Now, as long as you're consistent with your assumption for the entire problem, your answer will be correct. It may have a minus sign at the end, but that does not mean your answer is wrong. So if, let's say, we assign direction to I3 as going downwards, right? So if it turns out that I3 has a minus sign at the end, it does not mean that your answer is incorrect. It simply means the current flow direction that you chose at the beginning of the problem is opposite. But if the numerical value matches up, you will get full credit. It's important to keep that in mind. You might choose I3 as going down. Someone else might choose I3 as going up in the opposite direction. You might both arrive at the exact same numerical answer, but you might have a minus sign. One of you might have a minus sign. But that minus sign taken along with the direction that you chose does make sense. And so you'll receive full credit. Important thing about the assumption, as I said, you choose the assumption at the beginning of your problem, you stay with that assumption to the end. Okay, you do not change it within the confines of the problem. Otherwise, you will end up with the wrong answer. So if you chose I3 as going in one direction at the beginning of the problem, and you go to the next step and you change the direction, then you end up with the wrong answer. So you do not want to do that. All right, so you stick with the assumptions and the polarity of the voltages and the direction of the current at the beginning of the problem, and you will end up with the right answer. Make sense? Right? Okay. Current directions. We have reference directions. Where we have the ends of the circuit elements. Again, remember, current always flows through an element. Voltage is always across the 2 points, right? So when you choose the direction for the current, we use a notation, and the notation is based on 2 subscripts. Okay, it's called as a 2 subscript notation, and it notes the 2 points of that element. So in this case, in this example, it's A and B. If you're referencing current IAB, you're talking about a current that is going from point A to point B. Point of origin or point of entry into that element is the first subscript. IAB simply means current is going from from A to B. And conversely, if it's IBA, all you're doing is you're saying you're referencing current going from points B to A. For all intents and purposes, they're the exact same current, right? IAB is equal to minus IBA, or you could write IBA equals minus IAB. Mathematically, same numerical value. We just put a minus and plus sign so that we can solve that circuit. We can solve the circuit perform analysis mathematically. And that's why we put a plus or a minus sign. Otherwise, our equations would never balance out. Okay, so again, IAB simply means current flowing from point A to point B, and current IBA simply means current flowing from B to A. You would also sometimes see, let's say this element, which is shown to be a resistor, is known as R1, just as an example. So then you might also see something like this, IR1. Okay, in this case, IR1 is referencing, what is it referencing? It's simply referencing the current that is flowing through R1, but it has 2 subscripts, R1. It does not mean that it is talking about 2 endpoints. It is simply talking about the element which is named R1. Okay, IR1 could be IAB, or it could also be IBA. So just pointing that out. You would not encounter something like this often, but if you do, then you should know IR1 is simply referencing the name of that element, nothing else. All right. Okay, moving on. Voltage polarity is exactly the same. You have reference direction. We have 2 ends, A and B, for this voltage, right? A and B. If you reference VAB, you are referencing voltage, or you're measuring voltage at point A with your reference at B. Okay, VAB simply means you're measuring voltage at point A with reference to B. It simply means I'm standing at B and I'm looking at A. Does that make sense? Hopefully it does. So voltage VAB simply means I'm measuring voltage at A with my reference at B. If I was to put it in non-electrical terms, I'm standing at point B and I'm looking at point A. So again, I'm measuring the distance between A and B, but I'm measuring at point A, but my reference or my starting point is at B. And again, VBA is simply the opposite. Again, you're measuring the voltage at B with my reference at A. Numerical value is exactly the same. The only thing that changes is the plus and minus sign. So I could write VAB is equal to minus VBA, or VBA is equal to minus VAB. That's it. Again, the plus and minus sign is just so that our equations balance out on paper. That's all. This that you see right here is not often used. Sometimes we just use, so it simply states the positive is here where the arrowhead is. But I'm going to say never ever seen anything like this in an actual textbook or an actual, it used to be a long time ago, but for the most part, you simply see a plus and a minus sign. So if you have an element, it simply be noted plus minus like this with a voltage. If this is element A, you would simply say VA, voltage for element A with a plus on the left and a minus on the right. That's how it's usually noted. Sometimes if it's a larger circuit or the circuit schematic has like, very large, physically large description in the schematic, then we would point at something like this. So let's say then you would simply do something like this. You'd say VA, and we would point an arrow in both directions, and we would note plus and minus. Again, it's just different people use it differently, but the most common is what you see here on the left. VAB plus and minus, VBA minus. So it's the exact same thing. Even without the arrow, even without the arrows that I just drew in this example right here, all you need is the plus and minus sign. All right. Ohm's law. Assume that students have encountered Ohm's law in physics, perhaps even in high school. If not, again, we'll do a brief recap. I just like this meme. There are plenty of memes of Ohm's law out there, but I just prefer this one. It's basically if you have a voltage that is applied to a resistor, it's a potential difference. It's an electrical potential difference across two ends of the resistor, which will cause current to flow through. Again, remember I talked about how voltage is nothing but the difference in potential between 2 points. So if you apply 0 volts at one end and 5 volts at the other end of a resistor, current will flow through because there is a difference in potential. Current for a passive resistant, for a passive element, always goes from high to low. Gravity hails that everything that is at the top comes down to the bottom, right? Pressure always goes from high to low. If you have water at two different levels, it will always go from the higher level to a lower level. Temperature also flows from high to low. Similarly, electrical current flow always goes from higher potential to lower potential. So if you have a plus at one end of the terminal and a minus at the other end, current will always go from plus to minus, always from high to low, except when it is a power supply. For a power supply, it's the exact opposite. Again, we'll talk about it when we get to an example problem. But for the most part, for resistors, capacitors, and inductors, current will always go from plus to minus. So based on that, you have a voltage that is being applied to a resistance. You have current flow, and you have the resistance. So George Ohm, the physicist, came out with this equation. The equation simply states the voltage across a resistor is a direct product of the current that is flowing through that resistor and the resistance itself. So V equals IR. V equals I times R. Okay, let me simply write V equals IR. Voltage is the product of the current and the resistor. In terms of units, we have volts equal amps times ohms. This is the most fundamental of all equations in electrical engineering. You can solve all circuits with this equation. Now, when I say solve all circuits, I mean, if it's a simple enough circuit, you can solve it with Ohm's law. There are some circuits, and we will look at different analysis methods, which will be connected in such a manner that it would be impossible to apply Ohm's law. Okay, but all the equations that we learn, all the equations we study, they're all based on Ohm's law. Voltage is the product of the current and the resistance. V equals IR. If we have any of these two quantities in this equation, we can derive the third one, or we can calculate the third one. The current can be determined if you have the voltage and the resistance, and the resistance can be determined if you have the voltage and the current. Okay, easy enough. Right, any questions? Yes. So current is defined as the rate of flow of charge. So yes, you are right. The question being asked was, amperes is not a direct, amperes is of course just the unit for current, but current is defined as the rate of flow of charge. And so it is coulombs per second. There is, but there's a physical definition. It's rho L over A. Rho as in the Greek letter rho, for resistivity, which is a material property, and the length of the piece of the material divided by the cross-sectional area. So again, good questions, but they are related to the physics of things, and so we tend to stick to the electrical engineering side of things. But good questions nonetheless. All right, any other questions? Okay. All right, energy and power. Anytime we have an electrical circuit, we have a source and we have the load. A source supplies electrical energy, right? And a load receives or absorbs the energy. So again, law of conservation of energy applies. Energy that is supplied cannot exceed the energy that is being received cannot exceed the energy that is being supplied, and vice versa. If a source is supplying certain amount of energy, we have to account for everything. Okay. The energy that is being received by the components will always be less than the energy that is actually being supplied. Where is the rest of it going? Heat. Absolutely. Anytime you have electronic device, energy is being transferred. Whenever energy transfers, some of it is consumed by the receiving element, but some of it is also lost as heat, and that's why you have your electronic devices that get hot. Laptops, older laptops especially, used to get very, very hot. If you play any games on your smartphone, if you charge your smartphone, energy is being received or energy is being dissipated. In both cases, a lot of the energy is dissipated as heat. That's why it gets hot. That's why you also have massive heat sinks on the CPUs of your desktops. Okay, now not so much because you have energy efficient, processing microchips. But if you look up any, big desktops, especially gaming ones with powerful processors, you have massive heat sinks on them. It's because every tiny component would give out very, very small amounts of heat. That heat could be on the order of nanowatts or even picowatts, 10 raised to minus 9, 10 raised to minus 12. But if you have billions of transistors on one device, which is the case nowadays for most CPUs and microchips, then you multiply that by a billion or a trillion, and each picowatt or each nanowatt now is combining together to dissipate energy in the amount of like tens of watts. So again, just a practical example of when electrical energy is being transferred. But law of conservation of energy applies. Within a closed loop circuit, any energy that is supplied by the source is always absorbed by the element. In In practical terms, of course, you would have to calculate the amount that is being lost as heat and the amount that is being consumed. 201, if you remember, or if you recall, I said we only do theoretical analysis. So we do not calculate any heat. We only calculate the power and the energy that is applied to each element. Meaning if a source is supplying 50 watts and there are 5 resistors in there, depending on the value of those resistances, we simply calculate the theoretical power that is being received by each component. Okay. We apply the equation for power in electrical engineering as P equals VI. As simple as that, as the product of the voltage and the current. P equals VI. And this, in conjunction with Ohm's law, gives us 2 more equations. Okay, if you combine this with Ohm's law, which is V equals IR, you can use this to find the power for the resistor. We can obtain P equals I square R, or P equals V square over R. We're simply substituting V equals IR into our power equation. Then rearrange the terms, and we obtain this or this. You do not have to memorize these 2 equations where I say P equals I square R and V square over R. I mean, if you can remember them, that's obviously good. But if you cannot, that's fine. The only 2 things you need to remember is the Ohm's law and the power equation. All right, makes sense? So now we are talking about power that is being delivered, power that is being absorbed by the element, right? Or energy, sorry, energy supplied, energy being absorbed. Can a power supply deliver, like power supply, power adapter, your wall chargers, can they supply negative power, negative energy? No, right? Power has a physical basis in real life. Energy has a physical basis. It's not negative. We assign positive and negative so that we can balance out the equations and we can solve that circuit. So anytime a source is supplying power, if it's supplying energy, we put a minus sign in front of that number. Think of it as money. If you lend your buddy $100, you will most likely never see it again. Okay, so now you supplied something, you are out $100, your net balance in the account is minus. On the other hand, if you receive $100, which again, you know, it's a net positive. So again, if you are supplying, if there's an element that is supplying power, we put a minus sign in front of it so that we can balance out our equations. Otherwise, we would never end up with a 0. Okay, energy supplied has to equal all of the energy that was received. And that's why we put a minus sign in front of it. So when it relates, how it relates to voltage and current is that at the beginning of our analysis, we assume voltage polarity, we assume current direction, right? So if the current is entering the negative end of the terminal, as we show on the left-hand side of this illustration, so the current is entering the negative end. That means that energy is, the energy is being supplied. Again, minus sign, right? If it's minus, then it's being supplied because it's losing power, it's losing energy. So if current enters the negative direction, then energy is being supplied. If it enters the positive direction, as shown here, then energy is being absorbed. You're receiving the money, you're receiving the power, you're receiving the energy. So energy is positive. So again, whether the current direction and the voltage polarity are given to you or whether you make an assumption is irrelevant. Once you have the current direction, once you have the voltage polarity, you simply take a look at which direction the current is entering. So current enters through one end of the terminal, one end of the element and exits out of the other. And so if current enters the positive terminal, power is positive, energy is positive. If it enters the negative and the negative terminal, then power is negative, energy is negative. Make sense? So if power is positive, you use the equation P equals VI. If it's negative, use minus VI. So let's look at these examples on the slide. We have 4 of them. I just call them A, B, C, D, starting from the left. We have A, and because it's positive here, that means this end of the element is positive. Let me just put down A, B, C, and D. So current is entering the positive direction, positive terminal of A. And so the power equation we will use is P equals VI. Easy enough, right? Similarly, if we go to D on the far right, current enters the negative end of that element. And if it's entering the negative end, power is equal to minus VI. Or the equation, at least, is minus VI. That's the equation we would use. So A and D are easy enough. B and C, again, it's just drawn a little bit differently. But if you extend the arrow, again, remember, current needs a closed pathway. So if it's actually flowing in one direction in one path, you can extend the arrow and just solve it that way. So now we know for B, the current enters the positive terminal. So power equation we would use is P equals VI. Make sense? Right? And the same thing for C. You extend the arrow for the current. Current is entering the negative terminal and leaving out of the positive terminal. So power is negative. We use the equation P equals minus VI. Let's take a 10-second pause. You think over it. Let me know if you have any questions. Any questions? All right, let's look at examples. A, B, and C, we are already given the voltages, we are already given the currents, we already have the polarity and the direction of the current, polarity of the voltage and the direction of the current. So how about A? Positive or negative? Positive. Power is entering the positive terminal. So the equation we would use is P equals VI. You simply plug in the values, 12 times 2, and P is 24 watts. By the way, anytime you solve a problem, this is what I want to see. You first set up the problem, make your assumptions. So you have your direction for the current and the polarity for the voltage. Then you write the equation first. Then you plug in the values and then the final answer. Okay. It's just good habit as engineers to go step by step. Chances of making errors are reduced if you proceed step by step. And do not forget the units. Units are very important, as are unit prefixes. Okay, it's 24 watts. It could be 24,000 milliwatts, and you would still have the right answer. You would still get full credit. Okay. So again, your numbers should match up, and so should your unit prefixes, and so should the units. And then you receive full credit. Missing units would be -1. Any problem, any quiz, final exam, if you have missing units, it'll be -1 for every missing unit. The final answer should always have units. All right, how about B? Power is negative, so we use the equation P equals minus VI. Plug it in. Minus 12.1. P is minus 12 watts. Supplying or receiving? Supplying. Minus means supplying. How about C? Entering the positive terminal. So we simply use P equals VI. You do not make any changes to the direction or the voltage polarity. Okay, otherwise you will end up with the wrong answer. Simply determine which equation to use based on the information that is given to you. You plug in the value, you end up with minus 36 watts, which is fine. Your answer is not incorrect. Taken with the direction of the current and the polarity, if the numerical value is correct, you will receive the full points. You will receive full credit. But again, do not change assumptions in the middle of the problem. Okay. Right now, at the beginning of the problem, we have the information that the current is entering the positive terminal. So we choose the equation P equals VI, not P equals minus VI. But then if you decide, oh yeah, current is given as -3. So let me change this as minus and then remove the minus from this equation, you would end up with the wrong answer. Yes. So power is being supplied. So the question being asked is whether element C is supplying or receiving power. The final answer we receive is minus 36. And so the power is being supplied. So even though at the beginning of the problem, we think that, okay, the current is going in this direction, is entering the positive terminal. So power is at the beginning of our problem, the beginning of our assumption is that the power is being received, positive power. But at the end of the problem, we receive a negative answer. It only means that our assumption at the beginning of the problem was incorrect, but our answer is still correct. So again, I want each and every one of you to understand that if your assumptions turn out to be incorrect, does not mean, well, actually, wrong choice of words. Assumptions are not correct or incorrect by itself. It only means that the direction was opposite of what you chose at the beginning of the problem. But your answer will always be correct. It doesn't matter what you choose at the beginning. Does that make sense, or did I confuse you all a little bit? Okay. How do you say this name? Kirchhoff. The first time I heard it, I was in a department meeting and I was like, I have no idea what's going on. Why am I here? Someone help me out. In India, we call this as Kirchhoff. It's a German physicist. The actual German pronunciation for this name is Kirchhoff. None of us lived during those times, so we don't know how his name was actually pronounced. But if you ever hear me say Kirchhoff, well, this is who I'm talking about. German physicist who came up with a couple of laws regarding currents and voltages, brilliant equations. They are based on the law of conservation of energy, and they are both very well known by their acronyms, KCL and KVL. For the most part, I will use KCL and KVL. Now, the reason we go over these is because this class is built step by step. You know, you learn about Ohm's law, power equation, KCL, KVL, then you learn about node voltage analysis, mesh current analysis, maximum power transfer theorem, Thevenin and Norton analysis. And so students need to be very proficient at applying KCL and KVL quickly, efficiently, and correctly. Because the chapter 2 equations or methods are based on top of these. You will use these to derive equations for different methods. So again, even if you have done this before, I do need to ensure that each and every one of you can do this very, very quickly and correctly. Okay. So you may have preferred techniques that you have already learned in the past, whether in physics 3, whether in high school, doesn't really matter. I'm not here to force my techniques on you. If you have a preferred method, you can stick with it. As long as you can apply KCL and KVL correctly, that's all that matters. Okay. So what he said was, whether it's for current or for voltage, the sum of currents around a junction in a electrical circuit will always equal 0. And the sum of all voltages around an electrical loop will always sum up to 0. Again, law of conservation of energy. Everything has to sum up and balance out. So the way I apply KCL is basically, I take an equation and I look at the junction or the node. All the currents that are entering the node, I put on the left-hand side of the equation, and all the currents that are leaving the node, I put it on the right-hand side of the equation. And that's it, balances out. So if you take any junction, let's say IA, IB, IC, and ID. Currents entering this junction are IA and IB. So I put them on the left-hand side of the equation. So you get IA plus IB. And currents leaving are IC and ID. And that's it. You have my KCL equation. If this was a traffic junction, all vehicles entering a traffic junction have to exit. The sum of all vehicles entering a junction have to equal the sum of the vehicles leaving the junction. Otherwise, you'd have Die Hard 4. Anyone remember that scene from the movie? No one? Seriously? No Die Hard fans in here? The first 4 movies were still good. 5th one, not so much. But there's a scene in the movie where there are hackers sitting, and they change all the lights at the junction at green. So all vehicles go from all 4 directions. Electrically speaking, that would never happen. All right, that would never happen. Physical, again, electrical current and everything has a basis, has a physical basis in real life. So if you have electrons flowing in one direction through a closed electrical pathway, it would just be one direction. Anyway, coming back to KCL, it doesn't matter how you interpret this and apply a technique. If you have a technique, you can apply it however you want. You will end up with this exact same equation. It would be IA plus IB minus IC minus ID equals to 0. It would still be this exact same equation, right? So if you take a look at this problem right here, we are given the values of IA and IC, right? And we are asked to find IB, ID, and IE. IE is not explicitly asked, but again, it's easy enough to determine. So what do you see first on the left-hand side? Specifically with IA and IE. They are in opposite directions, but they're the exact same current, right? It's the same loop. Now, physically, as I said, there's no physical basis to have currents flowing in 2 separate directions in the exact same electrical branch. Mathematically speaking, I can simply write IE is equal to minus IA. Or IA is equal to minus IE. Doesn't really matter. Whichever equation you choose, you'll end up with the right answer. So minus IA simply means IE is equal to minus 6 amps. That's all. As easy as that. Same thing on the right. IC and ID are the same electrical branch, but flowing in the opposite direction. And so ID is equal to minus IC, which is minus of minus 2. So I get 2 amps. We are not concerned what the actual direction of IC is. Okay, let's Make that clear. IC as shown is shown to us or is given to us at the beginning of the problem as flowing in the left side, right? IC is portrayed as going towards the left, but the value of IC is given as -2 amps. We are not concerned with that. Okay, do not try to change the direction of the current. Say, you can if you want to. Again, you can change the arrow and then say IC is equal to 2 amps, which is fine. But I've often seen students get confused and they make an error in the problem. So I always strongly advise and strongly suggest, do not make any changes to what is given to you in the problem. Just stick with what you have and just write down the equations based on that. Okay, so ID is minus IC. The only thing left is to calculate IB. We have IA and IC coming in and IB leaving the junction. So I have IA and IC on the left-hand side of the equation. IB is on the right-hand side of the equation. Currents entering equal currents leaving. And so IA plus IC is 6 plus -2. And gives me IB as 4 amps. Let's take a pause. Think over it. Let me know if you have any questions. Yes. No. It doesn't matter. You're only looking at the mathematical equations. So IE, we determined is minus IA, right? So it's -6 amps. That's all. That's all we worry about. That's it. We don't worry about how it looks to the original direction of the current or it doesn't look. We don't worry about that. So IE is minus. It simply means IE direction is the opposite of what is shown to us. That's all it means. If you did try to solve ID, IB, and IE, it would still add up. So if you apply KCL at the bottom, I can say all currents entering equals all currents leaving. But in this case, we have IE, IB, and ID all entering the junction. Nothing is leaving. Die hard 4. All lights are green. Let's plug in the values. IE came as -6. IB we just found was 4. And ID was, where's ID? Oh, 2. Equals 0. There you go. So mathematically it balances out. Again, whether the information is provided to you or whether it's assumptions that you made at the beginning of the problem, you stick with those assumptions, you stick with what is given to you at the beginning of the problem. You do not change it halfway through your analysis. Okay, as long as you're consistent for the entire problem, you will end up with the right answer. If you change anything in the middle, that's where things go wrong. Okay, so don't do that. All right. There are some examples on the next page. I usually assign these as practice for students. They're simple enough, not too complicated. Just solve them. If you have any issues, you let me know, and we'll work through that. There is KVL. We will leave that for next class. We have parallel connections and series connections. Again, we'll just leave that for next class. All right, so we'll end class here today, and I will see you all on Tuesdays. Monday is MLK Day, is a holiday, so have a good weekend. If you have any questions, you send me an email. I have a few other things to get done this afternoon, so I won't be in my office. If you need to see me for office hours, send me an email. I'll answer your questions as best as I can. If not, we'll meet on Zoom. Okay.